Hi, welcome to this lecture on environmental adaptation of animals. On this second video on energy metabolism, we are considering now on metabolic scaling. So now we can understand that, how we can measure the metabolic activity directly or indirectly. But then how we can compare, is the lizard or the human more efficient on its metabolism? So how to compare the small animal and large animal, and how to compare ectotherm versus the endotherm. So how to compare it? We can have metabolic scaling or metabolism size relation, meaning the same thing, to use to compare the energy needs of different kind of animals. And when comparing middle wall, it's used maybe a little bit less than 200 grams of grass per week, and then the rhino is using 650 kilos of same kind of grass per week. So naturally the large animal is using more food, but when comparing on the weight, so if 30 gram whale is eating 200 grams, so it's eating about 6 times more than its body weight. Whereas this rhino is consumption only 1/3 of its body weight within the same time. So there must be something that these large animals are a little bit more efficient on their energy consumption. And this can be tested on the resting metabolic rate and to be put in compare it in different size of the animals. So the basal metabolic rate is not directly affected on the body mass, but when comparing 600 different mammals, it's been compared with and plotted by using least correlation to minimize the distance between each dot and the line. Then you can see that the basic metabolic rate is significantly smaller in larger animals. So if calculating from the 10 gram animal that then 20 gram animal should have twice as much energy used per hour, etc., then there would be a linear correlation. But as you can see, the actual statistically correlated basal metabolic rate is significantly lower. So larger animals are more efficient. And then the problem can be that, over here we have only animals from 10 grams to 700 grams. Then what about the rhino? So that's why in some cases we can also have a logarithmic scale. Then we can have weight-specific metabolic rate. So because the small animals are consuming more energy per gram. So it's an alternative way to present this, to divide the energy used per time with the weight of the animal. And this shows quite nicely that, the small animals have higher weight-specific metabolic rate, and similar regression can be found in all phylogenetically related animal groups. This is from mammals. The similar effects also in birds or amphibians or fish, etc. And even this is only from 10 grams to 700 grams. So if we have a larger variation, so it's quite often that in both directions it's in logarithmic scale. And how does it work? We have a mathematical model for it. It's very simple. Don't be scared. So it follows a simple logarithmic scales where we have a metabolic rate that is the same as constant A times weight that is put in the exponent P. So we have two experimental constant. Well, the equation actually can be a little bit too simple, especially for some cases or for some researchers, but it works at least in the educational purpose anyway. And this experimental constant has been measured in several animal groups, and so comparing the metabolism of large set of animals. And the B is quite near 0.6 or 0.7, and A is highly variable. It's higher in the metabolic active animals like mammals. So when comparing different kind of animals, we can see that over here 4 lines in exponential scale. On the U scale is the how much oxygen they consume per hour, and then on the X scale is the scale of the animal. And there's on the top of these lines there are birds and mammals, and they go pretty much in the same way. And then those 2 lines below them are lizard and amphibians, meaning frogs. So we can have, for different kind of animals, we can use the same model, but they have different A and a little bit different B. And this can be a little bit modulated, so it can be used as a weight specific. And in this, because the B is about 0.7, then the exponent is over here is about minus 0.3. So their correlation is negative. And you can see over here that in small animals, the birds are using more oxygen than mammals. Lizards are using more oxygen than amphibians. And so it's especially in the small animal size, the difference in the metabolic activity is important. But as you saw in the larger animals, it would not be so huge difference if it's a bird or mammal. It's more. So the small birds need more food than the small mammals. But also the same equation, it can be also modulated to compare also the maximal metabolic rate if you ever get on these. Okay, the logarithmic scale can be used to evaluate when the weight differences are enormous, like the bottlenose dolphin versus some ghost bats. They weigh completely different. The weight is completely in different scale, but they are all carnivore mammals, so they follow quite nicely on a single allometric relation. So large animals are using less oxygen per gram per hour than the small animals. Or it can be also used to compare the individuals, because often it's related on the body size. So the large individuals use less oxygen per gram per hour than the small ones, but it's written in capital because it doesn't always be that way. Okay, what are the consequences of metabolic rate differences? Over here we have the heart of horse, cat, and laboratory mouse. You can see that, okay, large animal has large heart. But if we are comparing the heart rate and the weight of heart versus the weight of the animal, we can see some interesting differences. So the heart rate is lower in the large animals, and the heart weight is pretty similar in similar animals of all sizes. So there's not so huge difference in whether it's a mouse or African elephant when comparing the how many grams the heart weight versus how many grams the animal weight. But if it's the laboratory mouse, it has to have higher heart rate to have more circulation because it's higher metabolic rate. Then this allometry has also ecological consequences. Over here we have some animals living in African savanna. And from these you can see the average when on the bottom one with the African elephant. This is the heaviest one. And at the same time, the average biomass of entire population, when you are calculating, okay, how many giraffe you have, how many elephants you have, and what is the average weight of them. And from them you can calculate the average biomass. You can see that the large animals also have more biomass because they are more efficient on their energy metabolism. Okay, then because the B is something between 0.6 or 0.7, it's been speculated now for 1 century that what is the parameter behind this. And actually it was demonstrated by Max Rubner to see that, okay, it's some kind of Rubner surface law. And he started from just the basic geometry. That, okay, the surface area decreases as the animal size increase. And therefore, the small animals, they have more surface area, they lose more heat, for which they must have then higher energy metabolism. But the problem is twofold. First of all, it doesn't tell why the bee also exists in the ectotherms, and even in mammals, it's more than 0.67. So if it's something else than from this geometric calculation, it can't be that way. And actually, this Rubner surface law is after invention, it's been forgotten and invented again several times because it's so obvious. And nowadays, the consensus is that actually there is no general rule. B is about similar, but even when we compare these values between mammal and the dinosaur, meaning the bird, they have different A and B. So it's not identical among the animal kingdom. So they seems to be that they are working in the same direction, but they are not the same. Okay, then the energetics is affecting on the food and growth. Because how well the animal can use the food, we can calculate it by dividing the absorbed energy by ingested energy. So if we humans, we are eating cellulose, about 0% is absorbed. But in the ruminants, like cow, about 50% because the other 50% is consumed by the bacteria. And then the growing animals, there's also gross growth efficiency or net growth efficiency, where to compare the chemical bond energy of tissues to either the ingested or absorbed energy. And this is something that is used for estimated, okay, when we are raising chicken, so at what time we should kill them for food, because after that they reduce the growth of muscles. Or what happens in the fish. So when the young Pacific sardines are very young, they use 80% of this absorbed energy in the growth. But then if they are 6-year-old, they only use 1%. Thank you.